Okay, so today, again, I will try to use a text box. Before, okay, we will talk about finite depth quantum circuits and also symmetry protected topological phases. Okay, so the idea is to, this is from papers written by C. Chen. The idea is to try to study phase transitions using quantum circuits. Okay, so circuits are made of gates. Okay, so circuits are made of gates. A lot of matrices represent gates, or you can say that the gates represent matrices. A little bit of research will show you that there are the poly matrices, there is the XYZ matrices, and they can be represented using quantum gates. Okay, now there are classical gates like AND gates, NOT gates, OR gates, XOR gates, whatever. So NAND gates. There are a bunch of gates. Dot. And there are quantum gates. Okay, so if you with gates, you can connect them and form circuits. A finite depth quantum circuit, FDQC, just means there are a finite number of layers. So I have a gate, these two connected, goes over here, and then let's see, this thing goes over, let's see, another gate right here, maybe this connected here, and then you have these two going down to something like this, and then maybe this guy also comes down over here, whatever, something like this, okay? This would be 3 layers, literally 3 layers. Okay, back to here. Now, suppose you start with a bunch of uncorrelated qubits, okay? So you have a bunch of qubits, they don't have anything to do with each other. You got a bunch of them. Call this a trivial. This is called a trivial product state, okay? Let's just call it state P, okay? Now, you have some desired end state Q. Okay. Do you need a phase transition to change P into Q? Do you need a phase transition to change P into Q? That is a question that condensed matter theorists, condensed matter physicists have been trying to, are trying to answer often. Okay, so there are 4 cases again. And I'm going to draw the matrix like this. Okay, so using finite depth circuit, okay, using finite depth circuit. And here, I don't really want to call it infinite depth, just that you cannot use finite depth circuit, okay? And over here, I will call this using only symmetry gates, or gates that respect symmetry, okay? And over here, using any gates, okay? All right, so there are 4 cases. So if you are able to use finite depth circuits to change P to Q, then the state Q is trivial. I don't want to say trivial, but like, it's not much of a phase transition going on. Trivial. Okay, now, if you cannot use it, and you cannot use finite depth circuits, so using infinite depth circuits, or just like circuits that grow and grow and grow in layers. But you're only using gates that respect symmetry. So we'll talk about that in a second. Then call this a symmetry protected topological phase. Okay, now if you cannot use a finite number of layers, okay, and you're also, so you can use any number of layers, and you're allowed to use any number of gates, okay, then we say that, and only then can you reach the state. Then we call this truly topological or real topological. Okay, so we already know that gates represent matrices. Okay, so gates represent matrices. So by using symmetry gates, I mean that we can only means that we are only allowed to use gates that commute with the matrices of the symmetry group of state Q. Okay. So state Q has a symmetry group. Okay. Now, due to representation theory, these groups, the elements of the group are a bunch of matrices. And so, if you only use quantum gates that commute with the symmetry group matrices, that's then you're up over here. Okay. Now, if you decide, hey, I'm just gonna use any gate, then you're over here. Okay. Cool. Here we say that P actually needs to undergo a phase change in order to get to Q. Okay. Now notice that I'm gonna call this 1, 2, 3, and 4. Okay. So only by not using finite depth circuits, okay? So only by not using finite depth circuits and using any gate are you able to move from P to Q? Okay. That means that you're breaking all constraints, okay? You can use infinite depth circuits or growing depth circuits, and any gate are you able to move from P to Q? This means that it was state Q is truly topological or real topological or intrinsic. It has intrinsic topology. Yeah. And yeah, this stems from Landau had a paradigm as to I've talked about how phase transitions occurred through symmetry breaking, but a lot of that was based on electrons that didn't really like feel each other, weren't really strongly interacting with each other. Not by strongly, I don't mean the strong force. But when there are strong fermion interactions, when the electrons actually feel each other, the effects of each other, then you have to try to add to the Landau paradigm, which is what Sichet has been doing. I think that was her most recent paper. And also due to this kind of like new classification using finite depth quantum circuits and symmetry gates and not using symmetry gates, Shinsei Ryu's his periodic table of topological insulators, which has 10 classes, might need some updating. And this helps a lot of engineers and like people who work with real life materials, kind of helps them search for and classify materials. And yeah, that is it.